Welcome to this exercise for the lecture Pattern Recognition and Machine Learning. In this video we will cover Gaussian mixture models, and for this we will first review the Gaussian mixture model or GMM basics, before we then look at the GMM training, the expectation and maximization algorithm. We will have 2 comprehension questions and we will finish with a Python demo. So let's go ahead and let's get started. I would first like to look at a regular Gaussian, a normal distribution. This one usually looks like this, and it's defined by our mu, which is the mean value, and sort of by the width, which can be expressed by the variance sigma squared. So sigma squared is the variance. And we know that with only those 2 quantities, we can describe the entire distribution. So fx of x equals then the normal distribution of x given by mu and sigma squared. And as a reminder, this stylized n, it represents the normal distribution. And what we just looked at here is a 1D Gaussian or normal distribution. Now we can look at something else, which is by itself not a Gaussian distribution, but we can have 2 Gaussian distributions next to each other. And then we can say, okay, well, this one has a mean value and this one has a mean value, and they both have variances. Then how could we mathematically express the overall distribution we see here? And it's very easy. We simply add the 2 distributions. So the normal distribution x depending on mu 0 and sigma 0, and the distribution depending on mu 1 and sigma 1. And of course, this is not all. If we added them together, then actually if we took the integral, it would be more than 1. So we actually have to weigh them. So we introduce weighting factors G0 and G1. And those G's are then called mixture weights, GK, where the K is then the mixture index. And this then already tells you that we actually have a Gaussian mixture model here. We have 2 different Gaussians which make up a more complex distribution. So we went from a 1D Gaussian to a 1D Gaussian mixture model. To generalize the idea of a GMM, I want to now look at a multivariate Gaussian. When we go from 1D to multiple dimensions, this means that we have to go from the scalar mu to a vector mu. So we have a mean vector, and we have to go from our variance small sigma to the matrix big sigma, which is our covariance matrix. And when we do this change, we can then define the multivariate Gaussian distribution. Our x is then a vector as well, so we have the normal distribution of our vector x given our mean vector and our covariance matrix. And this is then defined by 1 divided by 2 pi to the power of d half, where d is the number of feature dimensions. And the other thing in the denominator is the determinant of our covariance matrix and the square root of that. And this factor is multiplied against an exponential function. And in the exponent of the exponential function is minus 1/2 times our vector x minus our vector mu. And this difference is transposed, multiplied against our covariance matrix, which is multiplied with the difference vector x minus mu, but not transposed. And this is then the multivariate Gaussian distribution. All this previous information we can now use to obtain the multivariate Gaussian mixture model. And here the distribution is depending on multivariate Gaussians, so what we just looked at. And because we're looking at a Gaussian mixture model, we sum them together. We sum from k equals 0 up to capital K minus 1, where then capital K is the number of mixtures we're looking at. And to finalize the formula, we have to add our mixture index here to our mu's and our sigmas, and we add our mixture weights. And this is then the distribution function of the multivariate Gaussian mixture model. And if you want to look at constraints real quick, we have as a constraint that, of course, the sum over all mixture weights, it has to be 1, because we're still looking at a probability distribution, a density function. And therefore, it also makes sense that our mixture weights can only lie between 0 and 1. And this is then the theory of how we come from a one-dimensional Gaussian to a multivariate Gaussian mixture model. Now that we know what a Gaussian mixture model is, we can discuss how the model parameters are estimated. And this is usually done using the EM algorithm, where E and M stand for expectation and maximization. First, let's discuss the cost function. The cost function is actually a probability. Gaussian mixture models are statistical models, and we're looking at the probability of a observed feature sequence. So we're not looking at just one feature vector x of n, but this is a capital X, so it's the large feature matrix. We're looking at the probability of that given all Gaussian mixture model parameters, so our feature weights, our means, and our covariance matrices. See here that we don't have k, so it's the entire Gaussian mixture model. And the cost function is then that this probability is to be maximized. So keep this in mind. This is the all-important cost function of the EM algorithm. And like all the other algorithms that we already had with codebooks, here we also start with an initialization. This can be done in different ways. And then the second step is already the expectation, the E step. And what do we do here? We compute the classification probability. The classification probability tells us how likely it is that a feature vector was produced by one of those mixtures alone. This probability is given as gamma of zk of n, where zk is our latent variable, which tells us which mixture exactly we're looking at regarding our classification probability. So how is this probability computed? We're basically evaluating the Gaussian distribution of one mixture. So we're evaluating a mixture k, which is given by our latent variable, basically. So we're also taking the mixture weight into account, and we are normalizing this probability by the probability of the feature vector from the entire GMM. And this is then our classification probability, which we're then using in step 3, which is our maximization, our M step. You might have already noticed that all the 3 equations of the maximization step have something in common. That's why I want to introduce a helping quantity, which I call P accumulated. And we have this for every k, and it's simply the sum over n of gamma of zk of n. And when we have that helping quantity, we can look at our equations, and our mean update is then the sum over n of gamma of zk of n times our feature vector at time instance n, and this sum is then normalized by our helping quantity. When we look at the variance update, it's similar to the mean update, but with a variance equation. It's the sum over n of gamma of zk of n times then our variance computation or estimation. So our feature vector x of n minus the newly estimated mean vector times the same difference vector, but then transposed to get the covariance matrix. And this is also normalized by our helping quantity. And then the weight update is actually our helping quantity divided by the number of observations. And writing it this way with our helping quantity, you should understand a little bit more what is going on there in these equations, what they have in common, and what we're actually doing. And then the last part of IAM algorithm is also the abortion step, or that we check for abortion conditions. And like most algorithms, if those conditions are not met, we go back to here step 2 and we repeat. So step 2, step 3, check in 4 for abortion conditions again, and then maybe go back to 2 and 3 and do this all over again until some abortion condition is met and we actually abort. And this is then the quick summary of the EM algorithm, the training of a Gaussian mixture model. And this concludes the Gaussian mixture model basics and review. Now let's move on to the comprehension question section. And the first question is, what is the advantage of adding variance information to Copo vectors? And for this, I would like to look at a two-dimensional feature space. So we have feature x1 and x2, and I could say I want to perform a classification task, and then my first class would be here in yellow, so I can draw those circles, and I have a second class in green where I have a bunch more circles, but you can see that they're distributed a little bit different. We have a wider variance here in this class. Now, if I wanted to compute codebooks, and I just say, okay, I do a supervised approach here, so I have one codebook in each class, then this is basically the mean of that class. So we have this codebook vector and this codebook vector, and then the decision line, if you want to use those codebook vectors as a classification, then the decision line would be here, and you can see that left of the decision line I have quite a few green circles. So actually these green circles that would be classified as belonging to the yellow class. Now, if I added variance information, you can see down here this has low variance and this has high variance, then I can use this variance information with the same means to move the decision line somewhere like here, and then this would result in fewer misclassifications if I have knowledge about the variances of the clusters. Now, a second case I would like to look at, we'll stay with the two-dimensional case, is if I have overlapping classes. So I can have, again, a yellow class here, and then this green class. And if I wanted to have codebook vectors here as well, I would have one in the middle of the yellow class, and if we say it's sort of rotated, then I would have for the green class one on the very top of that cross, so they would be the identical codebook vectors. And if I then try to do a classification, I don't have any chance. The codebook vectors are the same. I really have a problem there. But if I use variance information, you can see because of correlation, sort of the covariance indicator here, it would sort of look like this, and for the green class like this. And if you just look at it, you can see that you only have a problem, they only overlap in the middle. So this part here would be correctly classified as belonging to the yellow class, and this part would belong to the green class, which is perfectly fine. And then only in the middle we would have a problem with our classification task, which here we would have to live with, but we have a better performance than if we just had the means of those clusters and we wanted to perform a classification. The second question is, how do the k-means and EM iteration steps compare to each other? So let's look at those two different steps that we have in each algorithm. In the EM algorithm, the first part is the E step, the expectation step, and this more or less corresponds to the classification step in the k-means algorithm. But what do we do there? In the EM algorithm, in the expectation step, we perform a soft decision what mixture of the GMM a feature vector most likely sort of belongs to. So we go from x of n, our feature vector, and we compute the classification probability gamma of zk of n, where zk was the late variable which took care of the mixture correspondence. And because we're looking at probabilities here, this gamma can then be in the range between 0 and 1 and could take any real values between those two numbers. When we then look at the k-means algorithm, there we don't do a soft decision but a hard decision. We don't look at probabilities, but we do say that feature vector, it really does belong to that Cope vector for the update at least. But if you really want to compare this step to the EM algorithm, we can also work with a gamma here, and we go from x of n to a gamma, but I'm not saying zk, but I'm calling it zi here. This wasn't defined in the lecture, but it has the same meaning as zk, but because we used I with codebooks, I'm using zi here. And if I then say this can't lie between 0 and 1, but it can take either 0 or 1, then this shows us the difference between expectation and classification, so between soft decision and hard decision. Then the other step is the maximization step in the EM algorithm, which is more or less the correction step in the k-means algorithm. And because we use soft decision in the expectation step, the update for the means in the maximization step is basically a weighted mean of all available feature vectors, where for the correction, it's more of a mean that we compute on selected feature vectors. But let's see what this was in formula. So the update for our mean was that we look at the sum over all feature vectors weighted by our classification probability, normalized to the sum of the classification probabilities. And then actually for the k-means algorithm, we can write it down in a very similar way that when we want to update our Cope vector ci, it's actually the same. So the sum over all feature vectors, but weighted with our gamma and then normalized to the sum of all gammas. And here you see that we actually have sort of the same formula for the mean update, but because we computed gamma in a different way, it holds a different meaning and the output is different. So actually what you should take away from this is really the difference between the soft decision, which is a probability, and the hard decision. And then when we want to finish comparing these two algorithms, of course, in the maximization step, we don't only update the mean, but we also update the variances or the covariances and the weights, which is then also a difference to the k-means algorithm, where we are simply only working with means, so with just the Cope vectors and no additional information. Now let us move on to the Python demo, where we will be looking at the expectation maximization algorithm and GMMs in general. First, let me run through the notebook for you before you can have a chance to complete it. At the top, we again import all the libraries that we need, and I have created a library GMM support where we have the k-means algorithm that we used in the codebook exercise and some other supporting functions that we're using. And then we're basically implementing the EM algorithm. And the first thing we need for the EM algorithm or for GMMs in general is that we need a function that for one feature vector, it gives us back the value of a Gaussian or normal distribution giving means and variances. This is the first function. And then the second function is that we actually compute the value of a GMM given a feature vector and the weights, means, and variances. This function isn't complete yet. You see a question mark there. So go ahead and complete this function. Then the next function is the cost function of the EM algorithm. So the logarithmic probability. And I want you to complete this function as well. And the next function is not the EM algorithm as a whole, but just one iteration. So both expectation and maximization. The expectation step is already completed there. You see that we compute the gamma, the classification probability, and then in the maximization step, we need to use that classification probability. And you also see question marks there. So please figure out how you use all the quantities you have with the classification probability to actually do the maximization update. Please also look ahead. We have a normalization there, so make sure that you complete the function in the correct way. Then the following function is then actually the EM algorithm, which will call on the EM step that we just completed. Of course, we have the abortion conditions at the end, but at the beginning, we also have the initialization, and we're initializing using codebook, so the k-means algorithm. And I want you to complete the initialization then not for the means, because this is then just the codebooks, but for the covariance matrices and the weights, because there you need to compute something. It's not just given by the codebook itself. And this is then all you need for the EM algorithm. And we have some applications here. First, we just apply to overlapping data, something we also saw in the comprehension question. And this is basically the data we will be working with. So we will see more or less the classification of those two classes. For this application, there's actually one function left that you need to complete, which gives us a decision based on a sample and pre-trained GMMs, basically a classification decision. And we will also see if it were one class, what the GMM will give us, what advantage we have, and then later on we will have more complex data and we will look at advantages of Gaussian mixture models. But first, complete the functions before I run you then of course through my implementation, and we can actually discuss all the applications here at the end, and I will go through those applications more in detail in the results section. The first function we need to complete is the GMM function, and this function calls on the normal distribution function that's already implemented, and we call this function with our feature vector and the mean and the variances of the current mixture. So we have a value of the normal distribution, and this we weigh with the weight of the current mixture. And when all this gets added together, we have a value for our GMM. Then the cost function, this is actually then the GMM evaluated with all feature vectors. So I need to call the GMM with the individual feature vectors. This is what we iterate over. And the GMM, of course, gets all the weights, means, and variances. And because we're looking at logarithmic probability or the logarithmic cost function, we also take the logarithm of those individual values. And this is also why we can add them all together here. Now for the maximization step. Here for the mean update, I take all samples into account. So I basically add samples here. But you know that we have to weigh them with our classification probability. And at this point in the code, this is enough for the means, because down there we're also normalizing them correctly. And for the weights, we know that it's the sum over all corresponding gamma divided by the number of feature vectors. So at this point here, we just have to add gamma in this loop. Now for the initialization of the covariance matrix, we need to perform a multiplication of two vectors. And it's actually the same vector, and it's the difference vector between our current feature vector and the selected copo vector. And they're the same vectors, but one of them has to be transposed. And then for the weights update, I just add a 1 to the selected weight. And this works because in the following, after this loop, we will also perform a normalization. So when we want to perform a classification, we have several Gaussian mixture models available. They're in a list, and we want to know in this list which GMM gives us the highest return value, which GMM has the maximum likelihood. So for filling in this question mark, it's basically the argmax of the probability vector that we create by calling on the Gmm function in our loop here. So let us apply the algorithm we've just implemented. We're applying it to artificial data. We're sort of creating this data in the way that we did in the copo exercise, but we're using a little bit different data to show you some other effects here. And we actually have two blobs. They're overlapping, they're correlated, but they have a different correlation, and they sort of form a cross. And we have two classes here. And on these two classes, we can then train two GMMs. This is in the function here. So we train one GMM with the blue data and one GMM with the brown data. And when we run it, you can see some output from the initialization from the k-means algorithm, and then some information about what is happening in the EM algorithm. And when we look at the plot, the red dots here are the centers, the means of the Gaussian mixture models. Here I also gave each Gaussian mixture model one Gaussian, so it's not necessarily a mixture, but we've estimated everything according to the EM algorithm. And I just wanted to show you that we actually estimate the variances correctly, because you see here with the ellipses, those are variance indicators, and you see that those indicators, they actually follow the data, meaning that we have the right correlation information in our covariance matrix. Now it's interesting what would be the classification performance if I took the same data and I wanted to classify all the data. For this we implemented the classify function, and when I throw all the data together without giving information on what class the data belongs to, then I get my prediction, and I can plot which data is correctly or falsely classified. And here in this plot I have red dots, and that's the data that has been falsely classified. And you see that we only have a problem where our classes overlap. And as I showed you in the comprehension question, this is because we have the variance information, and Copeland would have had problems here. Now I want to move to an actual Gaussian mixture model. So we can say, well, both the blue and the brown data, they're actually both belonging to one class. So we would combine them, and we want to train a Gaussian mixture model on that data. And we can say that, okay, we're just training one GMM, but we're now having two Gaussians in this GMM, so two mixtures. Then we can train this, and we see similar output. And you can see here that our EM algorithm is able to estimate two mixtures, and depending on initialization, but here we were successful, this will actually mirror the two individual classes. But you can certainly see here that overall this GMM with the means and especially the variances, it mirrors the overall data distribution. So we were able to model a more complex non-Gaussian distribution by our Gaussian mixture model. Now I want to move on to even more complex data. We're using the data from before as one class, and we've just randomly added some other data in, but it's all one class. And I want to now train models for each class. So we're training two GMMs. And when we look at the data, we can see for the blue class, we'll give 2 Gaussians, and maybe for the other class, we give 5. So we're allowed to do that. And then when we look at the results, we see similar results for our blue class, and we can see that on each blob of the other class, we have a Gaussian as well. So we can assume we have good data representation, and we can also do a classification here, and we can see which points have been falsely classified, and we can see that we were quite successful. Of course, in the overlapping areas, we do have a few problems. Now, if you want to do a modification, we can maybe change the number of mixtures that we allow for the second GMM. We can change it to 2, and we can run this again. And then we see that because we don't have as many mixtures, the M algorithm is then of course less successful in representing the data well. It still tries to represent the data, of course, but in this case, to achieve a good representation, I would say at least 3 mixtures would be necessary, because we have 3 separate blobs. So whenever you want to train a model for some data, it's always important to decide how many mixtures you want to use, because this will of course decide how good your model can be. That concludes this exercise video. Thank you for watching.